Gauss's Gauss's law for magnetism, which just says that the magnetic flux, the total number of field lines through a closed area, must equal 0 because any field lines that go in must come out. Remember, that's different than from an open area, right? So B dot dA through an open area is not necessarily 0. So a closed area would be an area that is doubled over itself or something, right? So if I had a magnetic field, if I had a dipole magnet, and I thought I was recording and I wasn't, so I'm not sure what I said. So let me try again. So if I have a dipole magnet, for example, and I want to know what the flux or the amount of magnetic field through an open area, right? This is just an area. This is not a Amperian loop. This is an area. It's a circle with area A, and I have a net magnetic field which is passing through this circle. I've been trying to draw my magnet as this orangey yellow color. So I have a net magnetic field passing through there. The flux through there is not 0. It's if I have a closed area, right? If it goes into the volume and then comes back out of the volume of some area, right? So I have to draw a closed area. So let's pretend this is a cylinder. And so now any magnetic field line that goes in must come out, and so the net flux through that closed area, and again, a closed area means it encloses a volume, is 0, right? So the flux is 0 through a closed area, but through an open area it is not 0. So in general, the magnetic flux is defined as shown here, and let's say that I had a magnetic field. Let's say that I have a magnetic field, the constant magnetic field of 3 Tesla. It's a pretty big field, but regardless, constant magnetic field of 3 Tesla, and I've got some area, wall or whatever that it's passing through of with a area of 0.05 square meters. And if that magnetic field is passing perpendicularly through that wall, then the magnetic flux is simply, it's going to be B dot dA. Dot product goes away because of perpendicularity, so it's just going to be B dA. Magnetic field is constant, so it's going to be B dA, and so it's just going to be B times A. And so the magnetic field, the magnetic flux is going to be 3 Teslas, 10.05 meters, which is 0.15 Tesla meter squared. Sorry, ran out of room. The flux, the magnetic flux is 0.15 Tesla meter squared. So that's easy enough to calculate. But now let me, this is a calculus-based class. We need to be able to do integrals. Let's think about a magnetic field that changes across the area. Let me do a different problem with magnetic field that changes across the area. So I'm just going to set up this problem for you because it's similar to a homework problem. But let's assume that I have a magnetic field through a rectangular loop, but the magnetic field is constant in the vertical direction, but in the horizontal direction it gets smaller as 1 over r. So in order to calculate this, we need to calculate the magnetic flux through a piece of area where the magnetic field is constant and then add it up for the rest of the loop. And what I mean by that is that if I want to find the flux, integral of B dot dA, B and A are parallel, so it's just going to be integral B dA. We can get rid of the dot product. But I want to find the flux. I need to find the flux for when B is constant and then add it up. What I mean by that is let's go ahead and take a slice. Take a slice. Now make sure I'm recording, okay. Take a slice that is dx. And along that slice, as long as it's infinitesimally small, we can assume that the magnetic field is constant, and so what we get is again, I'm sorry, I might have messed up what I was recording and what I wasn't recording. Might have seen all those changes happen, which were meant to not be recorded. But in any case, I'm going to find the flux, which I'm going to call d flux, right? Just the flux in that red segment. And that is going to be B times the area of the red segment, which is y dx. Okay, that's the flux in that red segment, and B is constant. And so then, therefore, I can add up the flux. The magnetic flux is the integral of all the d fluxes, which is the integral of by dx. Y is a constant, so I can take that out, and so I've just got b dx, and b changes as a function of x as 1 over r or 1 over x. So the radial direction was implied to be that direction, which is also the x direction. So I did, those are the same variable. And so we've got y times the integral of 1 over x dx. And then we would just have to integrate from 0 to the final, the width of the loop from 0 to x. So that would give us the flux in that dotted loop that has area x times y. I'm not going to do the rest of that integration for you. You can do it yourself. It's on the homework. Okay, I think this is an easy one. This is a matchstick puzzle. It wasn't easy for me at first, but anyway, so what you want to do is remove 3 matchsticks to leave you with 3 equal triangles. And they're not tricky triangles. They are triangles made up of 3 matchsticks each. So you're moving 3 matchsticks to leave 3 equal triangles. So if you want to think about it, push stop. If not, it's removing 3 of the outer matchsticks around the outside, 3 alternate matchsticks, any 3 alternate matchsticks. Let's say that one, and that one. So you're left with 3 triangles. So why does an elephant wear sneakers? So he can sneak up on mice. What do you call an elephant at the North Pole? Lost. Why did the elephant cross the road? Because the chicken was having a day off. I'm not sure those are funny. Probably they are, or they were to us when we were 10 years old. But in any case, there is a lot of elephant jokes on the internet.